Is K a vector or a scalar?
Why do we take the absolute value? Why can't we have negative curvature?
Well, this is the length of it. And it's because curvature shouldn't care if it's up or down or left or right. It doesn't matter the orientation of it. So you can imagine you have a straight line that has a zero curve, right? Then if it goes that way or that way, it's the same amount of curvature. Does that make sense? I mean, how much you curve a bar? Well, if we curve it this way versus that way, it's still the same amount of curvature to it.
So why in physics do we care if something is positively or negatively curved?
Well, because you do other things with it. So this describes the curvature, but then you can define a position, a direction, if the direction matters. So if it matters if it's convex or concave in relation to something else, then you can define a direction to it. Yeah. Let me start to try to catch up to you guys here. Some of you guys are like, well, that'll be easy, John. All right. So R prime is what? So the length.
Root 10?
Yeah, root 10, right? Because it'll be 9 sine squared 9 cosine squared makes 9 plus 1 squared is 10. Now you can imagine that this gets really gross if this doesn't come out to be a constant, because then this function would, because you got to take this guy's derivative next after you put this together, right?
Yeah.
So thankfully there is another way. I'm going to show you the formula. I am not going to do the derivation of it because I just don't want to. So there you go. So now this is going to be just this. 1 over rad 10. So rad 10 over 10. Negative 3 rad 10 sine t over 10. 3 rad 10 cosine t over 10. Is that cool? All right. Let me stop there for a second. Let me you guys. So I took the derivative of the vector function, found its length. The ratio of those two, of course, will be the unit tangent vector. This is a tangent vector. When you divide by the length of it, I can make a unit tangent vector. Makes total sense. And now for this guy, I just need to figure out the derivative, which is actually the idea behind curvature. How quickly is that tangent vector changing direction? And just to point out, it makes sense we use unit tangent vector because I don't want to change in the magnitude of the vector to come into play here. It's all about how quickly that vector is changing direction, not how quickly it might be changing length. So that's why I want to use unit tangent vector. So what's t prime?
0.
0.
Negative 3 cosine.
Yeah. And then so then I need that guy's length.
3 over root 10.
Yeah, because then you, yeah, exactly. Like, let's see, we get
3 tenths.
you get like 9 tenths cosine squared plus 9 tenths sine squared, and then 0, and then the square root of that is back to 3 over rad 10. I like it. All right, let me stop there for a second. Let me make sure everybody's kind of with me. Everything we've done so far is not that horrible at all. It's like Calc 1. Calc 1, Calc 1, Calc 1. Now it's like 3 parts to one problem. That's all a Calc 1 problem. Right?
Once you get the unit vector, why do you take the derivative again?
Say again?
Once you get the unit vector, you take the derivative again? And that gives
Yeah.
you...
Because the whole idea, do you see how this is related to concavity? Because the big ass T itself is how many derivatives of the original?
1.
1. And then I take a derivative of it. Oh shit, so somehow it is related to concavity in a way. You would expect that concavity would show up in something related to the curvature or something. So this t prime is not exactly r double prime, but it is related because t comes from r prime. And then I take another derivative of it. Okay. All right. So now, so what do we got here? So the length of that was
3 rad 10.
Yeah, 3 rad 10 over 10. Yeah, and the length of that one we already know is rad 10.
So 3
3 tenths, I love it. And that is the curvature. That is the curvature. Now, do you see how the curvature itself in this case is constant? Is that always going to be true? The curvature here of this thing is not constant, is it? Why does this one make sense that it's constant? It's a circle. It's symmetric in all directions. Just because I'm pulling it out doesn't change anything, really. Just makes it so it doesn't go insane retracing itself forever. Like, here, let me help you out, buddy. Oh, I feel like I'm doing something. Yay. Instead of just, oh my God, oh my God, oh my God. Do the homework, turn it in. Do the homework, turn it in. I like it. Cool. So there's multi-steps to this thing, but all the steps are pretty straightforward. I like it. Okay, so here's the alternate way. We're going to do this problem again using the alternate formula to this. Because I don't know if you guys picked up on what I said. Can you imagine if this would have been square root of 10 t plus t squared or something? Then you would have had that expression on the bottom of this, and then you would have had to take this guy's derivative. Do you understand how quickly that could get disgusting? And you're all like, dude, we understand about disgusting. Yes, okay. So here's an alternate thing, and I'm just not. Let me leave this here since that was our answer. Another form for the curvature would be this.
Is that a cross product?
Yes. Believe it or not, if what I just said occurs, it actually is preferable to do this. Because then you're just purely attacking the R. You don't have to make a T and then take T prime. You're just purely attacking the R over and over and over again. So let's try this out and see if we get the same answer. If you're curious, and I know this is really obvious. No, it ain't. When I was waiting for it. Page 905, they show you the derivation of it. I'm not going to. So let's see. We got R prime already. We need R double prime here, right? So what would R double prime be? 0. Negative 3 cosine t, negative 3 sine t. Is that cool? So we need those things. So we got R prime now. R prime was, let's see. Can you guys do this cross product for me?
Sure.
Whatever method you like. Some of you guys like determinant methods. Some of you guys have actually memorized the 1, 3, 3, 1 and all that kind of stuff. It's just cool by me. I don't have much space left in my brain, so I always just do this guy. To be honest. Right, yes. Oh my gosh. Let's see. 9 squared pi. cosine k, 0k, minus negative 9 cosine squared, so plus 9 cosine squared I, which looks nice, minus negative 3, so plus 3. Oops, yeah, I didn't have any j's from earlier. No, plus 3 sine j. Is that where you guys are getting? You never know. Boom. Okay, yes, good. And then pop, bop, bop. Yeah, okay. Let me stop there for a second. You guys remember that thing about, if you have sine and cosine, you got multiples of them, just make them S and C, dear God, right? Give yourself some more room on the paper. So what's this here? 9i. And so I get 9i plus 3 sine tj minus 3 cosine tk. So that is the cross product r prime cross r double prime. So I hear differently. So it's like we all got the same thing, or you guys just waited until I got something. So that looks good, John.
Is curvature different than acceleration?
Yes. Acceleration has a lot more. Curvature directly doesn't depend on t. Now I can reintroduce t back into things, right? Mm-hmm. Acceleration would be purely. What would acceleration be? It would be purely. Yeah, r double prime by itself, right? So you can see that it does show up, right? But it's not, so obviously they're not equal to each other. Acceleration has more to do with how quickly a particle will be moving. This is more to do with how quickly its trajectory is curving. So it's not exactly the same thing. One is more based directly on its motion. How is its position changing, its velocity changing over time. This one is more, how quickly is that trajectory curving? How quickly is that curvature happening? So they're not exactly the same thing. They are related, but they're not the same thing. Otherwise, why do all this? Right? We would say it already exists. Yeah.
It's kind of like acceleration in respect to speed-ish.
All right. Ish. Yeah. Yeah. Ish. Yeah. Okay. So what do we got here? We got r prime is there. Let me write it like this. Where'd it go? And I want its, well, we might as well put its magnitude up there. Sorry. What's its magnitude going to be?
Square root of 10?
No, on the top, sorry. So on the bottom, yeah, r prime was square root of 10 or cubed, so that'll be 10 rad 10. Is that cool? On the bottom. Now on the top, what's the length of r prime cross r double prime?
9 squared plus...
Yeah.
9, 18, square root of 18.
3 root 10.
So it's 81
Oh, yeah.
plus 9, so 90, and then rad 90. So I get rad 9 over 10, which is 3 over 10. Same thing, right? Now this specific problem, both ways took about the same amount of time. Maybe the cross product is a little bit harder. But that's just because this happened to be nice. Making this nice. The minute this is not so nice, this method is much better.
Like any other questions other than sphere with constant curvature?
Say again,
Are
sorry.
there any other questions other than a circle with constant curvature?
Yeah, it's trying to come up with something that would have constant curvature. It would have to be either circular or the constant tangent line because it's already linear. Which is not a very interesting one to look at. Yeah.
So I see where you got 81, but can you just explain what that
Sure. to find this length, it would be the square root of 9 squared plus that squared plus that squared. And of course, 9 sine squared plus 9 cosine squared is 9 times 1 is 9. I like it. Y'all like, yes, a trig identity. I remember. Yeah.
Whenever they give you a point, you want to set those up to your x, y, and z functions, and then get a t. When you all connect at that point, the shortcut through that.
Wait. Well, how do you mean give you a point?
So sometimes they'll give you like, find the
Curvature at a certain point?
At a certain specific point, yeah. So from there, you would just take that point and set it equal to your original RT for the x component, the y component, and z, and then get a t where they all validate that point.
Well,
plug it back into that.
you have to figure out what the t parameter would be at that point if they don't give it to you that way. Then you go through all this work.
So if you don't have that, then you just do it like that.
Exactly. And this one was not necessary because it's constant.
Right.
But there can be some, obviously, where this will be dependent on t. And then they have to either give you t or give you a way to figure out what t is. Totally, yes. I like it. So this is an example of one that's got constant curvature. It's really easy. Well, there. The one thing I just erased. If I had something like this, that has good sound effects and non-constant curvature, right? It's not very high, and then holy crap, and then it's not very high, and then holy crap. So yeah, you can have a curvature that is dependent on t, obviously. Yeah, you have to. This just happened to be a nice constant one, which is why it was easy to do it this way and this way. This way gets gross the minute it's non-constant, yes.
When we're doing our homework, which approach, should we use? Which thing should we look for to go, oh...
There's a couple of problems, a couple of sections of the homework that say use 9, which is this. Use formula 9, and some of them say use theorem 10, which is this.
Okay.
And if it just says do it, you can pick, because then it's not. Then it's up to you. Yeah.
So I'm getting the map, but trying to put it into like a picture, I have no idea. That's a parallelogram. The areas up top.
Yeah. This would be.
Okay.
Well, again. You can try to analyze, so this would be, the result of the inside would be a vector that's orthogonal to both the speed and the acceleration. So first, consider that.
Okay.
Do you see what I'm saying?
I can see that.
Well, and actually we're about to do something, well, maybe we'll just do a little bit more, related to sort of like what you're talking about.
Practice.
Sort of related to what you're talking about.
Okay.
It gives you a way to think about it. Okay.
Because I know I was struggling with that with the first.
Oh, okay.
That kind of getting that, not what the heck it's showing.
I got you. Okay, let's see. All right. Just a couple more things, and then I'll let you guys out of here. Now here's something interesting. Phi prime t is some constant. Yeah. What would this be? Yes. And just to give you a little hint, let's see on page. Where are you?
You can't dot product it, right? Dot product requires two vectors.
Well, all right. So what I mean is this. I'm sorry. Yeah. There you are. Okay. This is oh yeah, I don't mean, so my bad. I put this in there too early. Shoot. So if I given constant Let me say that. Yeah. Been given a constant vector function. So what would that look like? Well, r is the radius, so obviously this would be the easiest way to think about this is it would be where's the radius constant? What kind of thing? Circle or sphere or something, right? You kind of with me? So it's got some kind of constant length. Then what would this dot product be? So, and if you look at, let's see, page 898. Where am I? There. Yeah, why?
Because if there's no change in length of the vector, then r prime is going to be 0. Have a length of 0.
All right. So if there's no change, then obviously r prime.
0.
But you're thinking just because the vector function has a constant, how do I say this? A constant length, doesn't mean the pieces of that vector function are constant. Does that make sense? So I was trying to see if they had a specific example, because I can't really think of one right now. Yeah, but look here. Let me see. There. This here. In fact, this is something related to. I think this was the same one that I asked you to prove on the test. And some of you guys realize when I ask you to prove something related to vectors, you just have to create an arbitrary vector and then do stuff to it. And that's how you prove something. If you use specific numbers, then you haven't proven anything. It just happens to work for the numbers you picked. That's all you've shown. So to prove it that way, you have to pick every number that exists. I didn't give you enough time for that. So real quick, what is if this is true? What's r of t dot r of t? Or if this is true?
0. Constant square.
It would be what's the length of r of t squared? So that's going to be c squared. I like it. So that's here. No? Okay. All right, so let me put this up here. This is one thing we know. If this is true, then this is true. Got it. That's true. Right?
But that's the magnitude.
Yes. So what is RT dot RT?
Magnitude times the magnitude times the cosine of the angle between them, which is 1 because there's no angle.
Exactly. So it's the magnitude squared. So a vector dotted with itself is equal to the magnitude of that vector squared.
Yeah.
Cool. And you can just analyze it the way that Ben just did. Just put it in the formula. The angle between them is 0. I like it. So it's length times itself, because there's no component of it you have to take. It's the whole damn thing that lies in the same direction as it. I like it. Cool. Let me see where I'm going. Oh, so then I know that this must be, what's the derivative of c squared? All right, so I know this is 0, which means that over there must be. All right, let me stop right there. I know. Sorry, this is just in general. So we got, let's say, d dt, r prime dot r. Oh, sorry, r dot r prime is equal to r prime dot r plus r dot r prime, which is 2 r prime dot r. All right, let me stop there for a second. There's a point to this. All right, guys, cool with going this way. This is a constant, so its derivative is 0, which must mean that r prime dot r is 0 divided by 2. So therefore, r prime and r are orthogonal. I like it. And we let that, and Ben's like, way to catch up with me. But I want to show all the steps that get you there. That was exciting. Now let me see if I remember what the point was in the beginning. Oh. So when if I'm in 3 dimensions, how many vectors are orthogonal to the tangent vector, the unit tangent vector? How many vectors are orthogonal to it? 2. How do you define a plane? Just how do you define a plane?
X minus.
You must be given what 2 things? A point and a vector, because that vector is how related to the vectors in the plane. It's orthogonal. So let me ask the question again. How many vectors are there that are orthogonal to this vector?
A plane.
An infinite number then. How many vectors live in a plane? An infinite number of them. Right? Alright, let me let that sink in. I love this. But there's one specific vector that's orthogonal. In fact, now we know what is the length of this vector. What's the length of this? Is defined to be 1. Thank you. Voice from the the length of t is 1 because it's a unit tangent vector. It's got to be length 1. So the length of it is constant, meaning that t prime dot t is 0. So when I describe a normal, a unit normal vector to this curve, it's going to be specifically, so let me, not surprising when I use the letter n. So this is the unit, normal, yeah, unit normal, I love it. They have a longer phrase for that thing, but I'm not going to look it up. Is this. Now think about this for a second. When I take the derivative of a vector that's unit vector, is the result necessarily a unit vector? Oh shit. So if I have a unit vector and I take its derivative, the result is definitely not guaranteed to be a unit vector. I'm going to let that sink in. You guys are like, whatever, man, just please stop. Make it stop. So, if I have a unit vector, its derivative. So, see how, if it was, I wouldn't have to do this. But in general, I say that just in case the derivative did make it not a unit vector anymore. So, this is, I really want, what does this say? T prime is orthogonal. Alright. So, that's the tangent. The orthogonal one should be the normal vector. Normal vectors are always related to being perpendicular. The normal to a plane is the vector that is orthogonal to all the other vectors in that plane. I want the normal vector this. How many could there be? How many candidates are there for the normal vector this? Infinite number. Oh shit, that's a huge room and a lot of waiting and then calling people in and saying, you're not good enough for this role. So we said, screw it, let's use the one that makes the most sense. Its derivative is orthogonal to it. So we're officially going to call its derivative the normal vector. You know, and then if I divide it by length, then it becomes the unit normal vector. All right. I like it. Good. That's the face I want to see. If you're not sure, you should be like, all right. So what we just did is on page, what is it? 906? Thank you. Yeah, 906. So just wait, man. We got osculating planes coming up and binormal vectors and lions and tigers and bears. Shit. All right. That's enough for today, I think. (13.4) should be semi-easier because it's all what we just done, but in relation to motion. So velocity, acceleration.
Yeah, so you just choose that, the derivative of the tangent vector, just because it's kind of like the easiest one to find. Basically.
And it's the one that kind of makes the most sense. It's intimately related to this. So it's the one vector from all the vectors that could be that actually is related to this most directly. Yes. So a lot of what we do, there's a lot of groundwork, and then we use them. So this is part of the groundwork. We will use that exactly. Once we introduce the bind, which is the vector that's orthogonal to both of those vectors, and then we set up this whole system that's used a lot in engineering.
Like, I don't really know what we're doing for.
I'm sorry. Just right now, just defining. Like we define the unit tangent vector to be certain, and then now I'm defining the unit normal vector to be a certain.
So we're defining a way to always find a normal vector to a unit tangent.
We more define what the exact unit normal vector is, because there are a lot of possible candidates. We say that's the one we're going to call the unit normal vector.
So this is the unit normal vector.
To the vector function.
Unit.
There's a tangent to the vector function, and there's a normal to the vector function.
But it has this tangent function going in big T.
There we go. There's no such thing as variables. But when you would say that big T is the tangent to the function, big N is the normal to the function at every point.
Oh.
I like because you always have a tangent and a normal.
So for the cross product for this, I did minus and negative, so I just did a plus.
Yeah, but something went wrong. Let me see.